Okay, this is a little video lecture on numerical differentiation. Here, let me bring up some notes. I'll share the screen. Okay, so this topic is not in the Muller book. It is in the Levy book. The basic question is, well, why should we care about numerical differentiation? I mean, we understand that integration is hard. There are lots of functions that are hard to integrate, but there aren't that many functions that are hard to differentiate. So why do we need to worry about that? So the answer is that there's sort of two reasons. One is that sometimes the function itself is not really available. What you have is a set of data points, or you have a part of the graph of the function, but you don't have the formula for the function. So in that situation, of course, you can take these data points and interpolate a function that goes through them and differentiate that. And that's actually what is sometimes done, but that's not exactly the same thing as differentiating a function. And then the other big reason, and this is the real reason why this is important, is that numerical differentiation plays a very important role in the numerical solution of differential equations. So a typical differential equation is something like this: y prime equal f of ty, where y is an unknown function and t is, let's say, time. And you are given an initial condition and you want to solve for y. So you have to approximate the left-hand side of this equation by some numerical expression and use that to solve for y. And so what happens is that you end up with a bunch of data points, tj, yj, and the y prime is approximated numerically. So numerical differentiation is necessary for that. So let's figure out how you could go ahead and do this. So we have to go back to the basic definition of the derivative. The derivative, by definition, for a function f is the limit as h goes to 0. So think of h as being a small increment in x of f of x plus h minus f of x divided by h, right? So this is the definition of the derivative, which you know and love from your favorite calculus text. And so since this thing, as h goes to 0, converges to the derivative, obviously this is going to be an approximation to the derivative when h is small. But an important question, which calculus books usually don't discuss, is how good an approximation is that? In other words, how fast does this thing converge to the limit? If it converges very fast, this might be a good approximation. If it converges very slowly, it might be a useless approximation. So we want to know if this is a practical algorithm or not. And we want to know if there are other things that converge to the derivative faster than this particular expression, okay? So that's going to be the topic that we're going to discuss. And there's really one and only one tool in our toolkit for studying things like this, and that is Taylor's theorem with remainder. So as most of you remember, this is the hardest topic in Calc 2, and it's the one that everybody always gets a little bit hung up on, but that's really what we're going to need. So let me go over it again. So you remember that Taylor's theorem says that f of x plus h is equal to f of x plus h times f prime of x plus h squared over 2 factorial f double prime of x plus, here, sorry about the stuff that was written in by hand because the scanner sort of cut off the bottom of the page, up to h to the n over n factorial nth derivative of f. And then there's a remainder, which we'll call r sub n. Now, for good functions f, a function is called analytic if this is the case. Then this, if you were to take infinitely many terms in this series, the series would actually converge. And that's great when it happens, but that still doesn't answer the question about how fast it converges. If the function is not analytic, Taylor's theorem still gives you an approximation to f of x plus h, but what you need to know is how to estimate the remainder. And you probably went over this in your calculus course, but this is one of the things that is going to be crucial for us. So what we're going to use is what's called the Lagrange form of the remainder. So the Lagrange form of the remainder, after including n terms, looks like this. It looks just like what would be the next term in the series, which would be h to the n plus 1 over n plus 1 factorial. So you see that there? That would be what you'd have in the next term, times the n plus 1th derivative of f. But the difference is that instead of evaluating at x, you're evaluating at c, where c is some point that you don't really know about, which lies somewhere between x and x plus h. In the case where n is equal to 1, we used this once before, and this is basically the, I mean, this whole thing comes from a form of the mean value theorem. When x is equal to 0, for example, f of x plus h is f of x plus a remainder, and that remainder is f of x plus h minus f of x. So if you were to take that and divide by h, the mean value theorem says that that's equal to f prime of xi for some xi, and that would be an example of Taylor's theorem with remainder. Okay, so this xi lies somewhere in the interval between x and x plus h. In general, you don't know what the xi is, but you might know, for example, that if f is a smooth function, then on the interval you're interested in, the higher derivatives of f are bounded by some constant. So you might have an upper bound for the numerator here. And then this at least gives you an upper bound on the error, which is all we really care about. Okay? So now we're interested in approximating f prime. Later we'll talk about higher derivatives, but suppose f has a continuous second derivative and we take n equal to 1. So then we have f of x plus h is f of x plus h f prime of x plus h squared over 2 f double prime at xi, where xi is somewhere between x and x plus h. So if we rearrange this, that tells us that f of x plus h minus f of x, I'm going to take this and move it over to there, then divide by h, so then that gives us an f of x, f prime of x on the right, plus this thing divided by h, which is now h over 2 f double prime of xi. So that tells you that if you take this thing and subtract f prime of x, so this thing over here is the error in approximating f prime of x by this difference quotient. That error is given by this formula over here. So in particular, it's bounded by m over 2 times h, where m is the maximum value of the absolute value of the second derivative of the function on the interval you're interested in. So that tells us that the difference quotient over here converges to f prime of x at a rate that's roughly proportional to h. Notice that this thing is roughly proportional to h. So as h gets smaller, the error goes down, but it doesn't go down all that fast. What we say is that f of x plus h minus f of x divided by h is a first order approximation to f prime. And that just means that the error is roughly proportional to h. Now, you might ask the question, can we do any better than that? So let's take this same formula over here, but replace h by minus h. And then we had the original formula, which had the h in it. And now here's the same formula with h replaced by minus h. So remember, when you change the sign of h, you don't change the even powers, you only change the odd powers. Those change by a sign. So this term changes sign and this term changes sign. Okay? And there's a xi1 in this formula, xi2 in this formula. The xi1 and the xi2 lie in their respective intervals. We don't really care very much about what their exact values are. But if you take this second formula and you subtract it from the first formula, then what you get is f of x plus h minus f of x minus h is equal to, or now all the even powers of h cancel out. So these two terms cancel out, these two terms cancel out, and over here this just picks up a 2. So you have 2h f prime of x plus h cubed over 6 times the sum of f triple prime at c1 plus f triple prime at c2. So if you divide by 2h now, that tells you that this difference quotient, this is what's called the symmetric difference quotient. It's the value between f a little bit bigger than x and f a little bit less than x. And notice the symmetry around x. And you divide, so you take the difference between those two f values, divide by the length of the interval, which is 2h, and subtract f prime, then that thing is, when we divide it by h, this h cubed now becomes an h squared. And we divided by 2h, so the 6 became a 12. So on the right-hand side, we have h squared over 12 times this number over here. So in other words, the symmetric difference quotient is a second-order approximation to the derivative. It converges much faster than the one-sided difference quotient, f of x plus h minus f of x over h. So what we learn from this is that if you want a numerical approximation to the derivative, this is a much better formula to use than that. Okay, so notice the important role that Taylor's theorem with remainder played here. If we didn't know about that, you might guess that all these formulas are pretty much the same, but they're not. So the lesson is that, you know, the order of the approximation is very important. When you have a second order approximation, it converges much faster. Just as, for example, if you remember when we were solving equations numerically, we talked about the bisection method, which is a first order method, and then we talked about Newton's method, which is a second order method, and that converges much faster. Okay. So that's the basics of numerical differentiation. Be sure to read the relevant section in the Levy notes, and there's also a section in Brin's book, and that sort of covers the fundamentals.